Hello everyone. In this lecture, we'll see the different DC motor characteristics. So here in this lecture, we'll discuss the three types of the characteristics. The first one is the torque versus the armature current. The second one is the speed versus armature current, and third one is the speed versus torque current. So this torque versus armature current is also known as the electrical characteristic, and whereas the speed versus torque current is also known as the mechanical characteristics of the DC motor. And in the previous lecture, we have set up the two relation between the torque and the speed, and we know that the torque is proportional to flux into the armature current. Similarly, the speed is proportional to the back EMF divided by the flux. So the speed is inversely proportional to the flux and directly proportional to the back EMF. So firstly, we'll take the DC shunt motor, and we know that the DC shunt motor, the field winding is placed in the parallel with the armature winding, and its circuit diagram looks like this, that if I'm giving a supply, so this supply will have shunt winding, which is a field winding, and in parallel we have the armature winding. So similarly like this, and this is your applied voltage, and this is the field current goes into the field winding, and this is the armature current. So here we can see that irrespective of load, if I'll place the load on the DC motor shaft, and if I'll just rotate the DC motor shaft, and if I'll just place the load on the DC motor shaft, IA is going to change, the armature current is going to change, and the field winding current, which is the ISH, remains constant. So taking this into account, let's first draw the electrical characteristics, or the torque versus armature current characteristics for the DC shunt motor. So it is like, we know that the torque is proportional to flux into IA, and we know that the flux depends on ISH here, because this is the field winding, and ISH remains constant irrespective of the load. So therefore the torque is going to proportional with respect to IA only itself. So taking this, if I'll just draw the characteristics, I get a straight line over here. So this is my straight line, torque versus the armature current, and it gets a straight linear line. However, this is the generated torque by the motor, and the torque available at the shaft will be slightly less than the torque generated by the motor due to the losses and the friction and windage losses. So therefore it is slightly less than my torque generated in the armature, and the shaft torque is slightly less than that. So this is the electrical characteristics of the DC shunt motor. Similarly, the speed versus armature current, the speed is proportional to EB divided by phi. We have already established this relation, and we know that the flux is going to constant for the DC shunt motor, because the windings are placed in the parallel. So therefore the speed is only proportional to the back EMF, and ideally the back EMF remains constant irrespective of the speed. However, as I increases the load, uh, there is one phenomena occurs in the DC motor, which is the armature reaction. So because of that, the EB slightly gets dropped. So therefore the speed of the DC shunt motor from no load, here I is 0, and going to towards the full load, my speed drops 5 to 15% depending on the motor capacity. Otherwise, ideally it remains, if I'll just take the ideal characteristic, it remains constant. And therefore the DC shunt motor is also known as the constant speed drive. also known as the constant speed drives. So the load applications where I need the constant speed drives, irrespective of load, if I increase the load or decrease the load, my motor should run on the same speed. So for such applications, I will use the DC motor. And the last characteristics for the DC motor, which is the mechanical characteristics, the speed versus the torque. We have already established the two characteristics, that torque increases as I increases the IA linearly, and the speed remains constant with respect to the EB, and it slightly drops. Similarly, that TA is taking directly proportional to the IA. So if I'm increasing TA, IA is also increasing, and we have already seen that IA versus speed characteristics. So the torque versus speed characteristics is also slightly decreasing from no load to full load. The next motor is the DC series motor, and in the DC series motor, the field winding is placed in series with the armature winding. So it is like this. My series winding is in place with the armature winding, and therefore if I'll apply the voltage, and let's say this is the field winding resistance, and here I have the armature, and this is the back EMF occurring over here. So if I'll just increase the load on the DC shunt motor shaft, here IA gets increases, and this IA value is same which also going into the field winding resistance, because both the windings are in series. So therefore whatever load current is being drawn by the motor, the same current is also going to the field winding of DC series motor. So I can say that as the IA increases, similarly my phi is also increases, because phi is proportional to the current which is going to the field winding, and the IA is the current which is going into the field winding in case of the DC series motor. So taking this into account, let's draw the first characteristics with it, which is the torque versus current, IA current, and we know that the torque is proportional to phi into IA. So here IA is a variable, and the flux also depends on your IA for the DC series motor. So I can say that the torque is proportional to IA square. So taking this, we can draw the characteristics now. So we have something like the square of this characteristics over here. So TA is square proportional to the IA square, IA, and as previously discussed, the shaft torque will be slightly less than the armature torque. So therefore this is my shaft torque, which is slightly less than the armature torque. And this is the dotted line which is shown over here is the characteristics which we have seen for the DC shunt motor, where the torque is linearly proportional to the IA. So here it is very much clear that the DC series motor produce a high starting torque, because the torque is proportional to IA square, and after some extent, if I'm keep on increasing the IA, my magnetic field windings or magnetic field gets saturated, and it will not further increase my torque, and then it will become proportional to the only IA after reaching the saturation. So I can say that then it becomes this kind of a characteristic. After reaching to this, then it will linearly increase with respect to IA. So there's such applications where I need the high starting torque to run a particular load. So there I will use the DC series motor. DC series motor, the next characteristic is versus the speed and IA. Earlier we have seen that the DC shunt motor is the constant speed drive, whereas the DC series motor again taking this expression that speed is proportional to the EB by phi, and we know that as I'm increasing the IA, my flux is also increasing because the field winding plays in the series. So therefore, the speed is inversely proportional to the phi. As the speed increases, or as I increase the further the armature current, the armature reaction takes place, it gets strong and the EB further gets dropped. However, the drop in the EB is very less as compared to the reduction in the flux. So therefore, I can say that the speed for the DC series motor is inversely proportional to the flux. So taking this, I can draw the characteristics now that my speed is inversely proportional to the here IA. So as I'm increasing the load, the speed of the DC series motor gets dropped. And the last characteristic for the DC series motor is the mechanical characteristic. Here, similarly, taking the speed and the torque, and previously we have seen it that the torque is proportional to IA square over here. So as I am increasing the torque, my speed gets gets dropped uh, like this in this pattern, because torque is proportional to I square and the speed is proportional to 1 by 5. So therefore, this kind of characteristics we get for the DC series motor. This means that if I'm increasing the torque, my speed gets dropped very quickly for the DC series motor. Now the third type of the motors are the compound motor, and here we are going to take the two types of the compound motor, which is the cumulative compound and the differential compound. We know that the compound motors are where I place my uh, field winding in parallel as well as in series uh, combination of with respect to armature. So this is kind of a circuit diagram I have made over here. So this is the shunt resistance of the field winding, and this is the series resistance of the field winding I have taken over here. So if I apply a voltage, the shunt field winding resistance remains, or the shunt field winding flux remains constant over here. So let's say that RSH is producing 5SH flux and the series field winding producing the 5SE flux over here. So cumulative compound motors are those motors if these two flux are adding each other, then it becomes the cumulative compound motor. Similarly, if these two flux are opposing each other, then it becomes my differential compound motors. So let's take one by one these motor and see the characteristics. So first characteristics is the IA versus the speed characteristics. Taking again that expression that and speed versus the armature current, and taking this expression that speed is proportional to EB divided by phi. So here, if I'm taking the differential motor, therefore it means as I'm increasing the IA, phi SH, the flux produced by the shunt field winding remains constant, and phi SE is going to increase because IA is also getting increased. And if I'm taking the differential motor, which is that they are opposing each other, so my flux is getting dropped down. So if my flux is getting dropped down, my speed is for the differential motor is going to increase with respect to the IA. Similarly, I have taken the reference over here. The shunt motor speed remains constant with respect to IA, more or less constant. And for the cumulative motor, these two flux are going to add each other. And if I'm going to increase IA, phi SE is increasing, and therefore the total flux is also getting increased in case of the cumulative motor. So therefore my speed gets dropped with respect to IA. Similarly, the torque versus armature current characteristics, and we know that the torque is proportional to phi into IA, and phi in case of the cumulative motor is going to increase with respect to Ia, because ISH remains constant and IS is going to increase, and for the cumulative motor they are both heading each other, so therefore it is going to increase. So I can say that the torque will be proportional to the uh, somewhat less than Ia square, so therefore the torque versus the Ia characteristic is similar like this, whereas the shunt motor has the linear characteristics, and for the differential they are going to oppose each other, so therefore the overall torque is going to decrease as I'm increasing the Ia, and therefore again here it is decreasing, Ia is getting increasing, so somewhat it is getting linear, but at the higher value of the Ia, this is going to decrease because my flux gets decreased significantly. And the third characteristic is the speed versus torque. For the cumulative motor, I know that the speed is proportional to EB divided by phi, and the torque is in case of the EB, which is proportional to phi into Ia. So in case of the cumulative motor, the flux is getting increased, Ia is also getting increased, so my speed is gets decreased with respect to the torque. Similarly, for the differential motor, my speed is going to increase with respect to the torque. So it says that if I'm increasing the torque for the differential motor, the speed is increasing, and for the cumulative motor, the speed gets decreased. So based on these two motors and based on the characteristics, the cumulative motor finds the application in many for the many practical things, because it gives me the sufficient amount of the starting torque. It also the speed is remains somewhat constant with from no load to full load applications, whereas the differential motors find the application mostly in the research work. For the research work only, it does not find any significant practical applications. So here discussing at last the applications. So here the DC shunt motor, as we know that it is a constant DC speed drives. So it is being used in the lathe machines, centrifugal pumps, fans, blowers, conveyor belts, lifts, spinning machines, etc. Whereas the DC series motor, which has the characteristics of giving the high starting torque, so therefore it is being used in the electric traction, hoist and lift, cranes and rolling mills. Similarly, for the DC compound motor, specifically only the cumulative compound motor, it has the application in elevators, rolling mills, punches, shears and planers. So there is one thing which you need to keep in mind, that DC series motor should not be started on the very lightly loaded and no load condition, because the speed is proportional to EB divided by phi, and if I am starting the DC series motor on very light load condition or no load condition, my flux will be very weak and the speed of the DC series motor will be dangerously high, and which can uh, which will have the my rotor will break the centrifugal force, and the motor can fall apart. So keeping all these things into mind, we have seen the characteristics of the all DC series DC motors, DC shunt, DC series, and the compound motors, and we have also discussed the application in here. Thank you.